Have you ever wondered how a machine actually learns to make a choice? I'm not talking about a coin flip, but a really complex prediction, like, is this tumor cancerous? Or what's a student's GPA going to be? Well, today, we're diving into one of the most powerful and, believe it or not, one of the most intuitive tools in all of machine learning, the decision tree.
You know, at its core, a decision tree is really just a flowchart. That's it. It's a model that makes its decisions by asking a series of simple, one-at-a-time questions. It's kind of like playing a game of 20 questions, where every single answer you get leads you down a new path toward the final conclusion.
Okay, so let's start with a classic example, just to see how this works. We want to decide if we should play tennis. So we start at the very top. First question, what's the outlook? If the answer is overcast, awesome. The decision is yes, we play. But if it's sunny, we have to move on to the next question. What's the humidity? And if it's rainy, we have to ask about the wind. See? Each answer just guides us down a different branch until we hit a final, simple decision.
Now, to really get how these trees are built, we need to know just a couple of terms. That very first question, in our tennis example, what's the outlook, that's called the root node. Think of it as the starting block, where all of our data is just sitting there before we make that very first split.
So from that root, we start to branch out. Any node that asks another question, like humidity or wind, that's called a decision node. It's just a point where the path forks again, splitting our data into even more refined groups based on some other feature.
And finally, when you run out of questions to ask, you arrive at an answer. These endpoints, the yes or no in our little tennis game, those are called leaf nodes. They represent the final prediction for any single path you could possibly take through the tree.
So, that tennis example, it was simple enough that you or I could have drawn it out. But here's where the real magic happens. The power comes when we let a machine build the tree for us, learning the absolute best questions to ask by analyzing a whole data set automatically.
Okay, so how does the machine choose which questions to ask? This is the most important part. Imagine all our data is just a big jumble of orange squares and blue circles. A bad question, a bad split, leaves them all mixed up. But a good split separates them into groups that are as pure as possible, right? With mostly blues on one side and mostly oranges on the other. The algorithm's entire job is to find the one question that creates the purest possible groups at every single step.
And this slide shows the connection perfectly. Every time the tree asks a question and makes a split, it's basically like drawing a line and chopping up the data into smaller and smaller rectangles. So a decision tree isn't just some abstract flowchart. It is a literal map of how the algorithm carved up the data to make its final predictions.
Okay, now let's see how this exact same logic can be used for something with, real-world, high-stakes consequences. We're going to go from predicting tennis games to classifying medical data. And this is where decision trees can be incredibly powerful.
This is the exact problem that researchers tackled in the study we're looking at. They took data from hundreds of patient biopsies, and they asked a simple question. Can a decision tree learn the patterns that separate a benign, non-cancerous tumor from a malignant one?
And here it is. This is the actual tree the machine built. Now, I know it looks way more complicated, but the logic is identical. It's still just a series of questions. But instead of outlook or wind, it's asking about clinical measurements like cell uniformity or clump thickness, which is see here as V1, V2, and so on, all learned from almost 700 real patient samples.
Let's just follow one path to see how a diagnosis gets made. The very first question the model learned was the most important one. It's about uniformity of cell size, or V2. Now, if that value is less than 2.5, the path stops, right there. The model is so confident, it classifies the tumor as benign, and that's the end of the line.
So, how well did it do? Well, after building and refining this tree, the model achieved an accuracy of about 95% on new data that it had never seen before. That is a pretty powerful demonstration of how effective this method can be in the real world.
So far, we've been classifying things into categories, yes or no, benign or malignant. But what if we want to predict a specific number? Well, that's where the other type of decision tree comes into play.
And this brings us to a really key difference. What we've been looking at is a classification tree. It sorts data into different bins, like benign or malignant. But a regression tree, that predicts a continuous value, something like a price, a temperature, or in our next example, a student's grade point average.
So let's check out another case study. The goal here was to build a regression tree to try and predict a student's college GPA using data like their high school GPA, their SAT scores, and the credits they'd earned. And here is the tree that came out of it. Notice the difference? The logic of splitting the data is exactly the same, but look at the leaf nodes, the final outputs. They aren't categories anymore. They're specific numbers. So for example, if a student's high school GPA is less than 2.835 and their verbal SAT is over 515, the model predicts their college GPA will be 2.818. Every path ends with a specific numerical prediction.
A single decision tree is pretty powerful, but it does have a weakness. It can sometimes get a little too focused on the specific data it was trained on. So, to make them even more accurate and reliable, a really brilliant new approach was developed.
Yeah, you can probably guess. A whole forest of them.
This is the whole concept of a random forest. Instead of building just one tree, the algorithm builds hundreds or even thousands of slightly different trees. Each one gets to see a slightly different piece of the data. And then, to make a final prediction, it just takes a vote or averages their results. It's basically like getting 100 different expert opinions before making your final call.
There's a great quote from the research that just perfectly captures the spirit of this idea. A group of weak learners come together to form a strong learner, thereby increasing the accuracy of the model.
Now, one of the coolest things about decision trees and random forests is that they are not a black box. We can actually look inside and see what the model learned was important to make its decisions. This chart here is called a variable importance plot. It comes from that random forest model we were just talking about. And it literally ranks every piece of information we gave the model, from most predictive to least predictive. We can see exactly what factors the machine was leaning on most often to make its choices.
So, for predicting a student's college GPA, what did the model find was most important? Well, no surprise, high school GPA was number one by a long shot. But what's really interesting is what comes next. The number of humanities credits they took in high school and their verbal SAT score were also highly predictive, even more so than some other factors we might have guessed were critical.
So, we've seen how a simple game of questions can scale up into this incredibly powerful predictive tool, used for everything from medical diagnoses to academic forecasting. The process is logical, it's transparent, and it's really effective. And that brings us to the final, crucial question. Now that we understand how they work, which choices are we ready to trust them with?